I am Professor Joe DalSanto, and I teach astronomy here at College of DuPage. But I have also been the chair of the Earth Science Department for a number of years, and so also teach quite a bit about the Earth, the other planets, those types of things. Been here at College of DuPage since 2012. How could we possibly know that? Sure, there are some relative ages we might be able to determine. Obviously, if we dig deeper into the ground, most people will understand that we're going to be going back in time, essentially, that what happened in the past. Archaeologists do that kind of thing. They have to find other ways to date what they find. But in the earth sciences, we have a way to find the absolute date of the age of the Earth. I'm going to describe to you a method to do that. And basically, it involves the way that elements change over time. Most people have heard that there are elements that are radioactive. In other words, they change from one form to the other. And the idea is we can measure very carefully how well they will change over time, the rate really at which they change. I'm going to refer to just a couple of slides here, but we're going to use, for example, two elements, one potassium, one argon. And you can see in my first slide here that, again, if we start out with a sample of potassium, perhaps a rock that is rich in potassium, we can measure how it changes over time. Now, we choose these two particular elements because they have a very slow rate of change. Some elements change faster. We can use those to date certain objects from not so long ago. But when it comes to the age of the Earth, it's quite ancient. And as a result, we need an element that changes very slowly. Well, you can see here that the potassium will gradually change. And you can also see, if you look down at our horizontal scale, the time in billions of years. That's quite a long time. Okay, let me go ahead and explain what we call a half-life. If we had, for example, a pure sample of potassium, and we were able somehow to sit around for 1.25 billion years, we would find that half of it has changed into argon. Now, of course, we can't do that, but we can measure the rate at which it changes and come to that number. If we waited around for another 1.25 billion years, we would find that, again, half of the remaining potassium would change into argon. So now we are at basically 75% potassium, 25% argon. I'm sorry, I said that wrong. 25% potassium, 75% argon. And you can see again from our graph how that would work. If we waited another 1.25 billion years, 3 half-lives would have passed. Now we would be down to merely 12.5% potassium and the remainder argon. So earth scientists, physicists, and other scientists have been able to use radioactive decay to date things. So how do we use that to find the age of the Earth? Well, simply put, we want to find the oldest rock we possibly can, the one with the least amount of potassium left in it. Now, what we have found on Earth is rocks of the approximate age of a little over 4 billion years. Until recently, the oldest rocks we had were approximately 3.8 billion years. But in recent years, we found a few more, just a bit older, right around 4 billion years old. So is that how old the Earth is? Well, not quite. It's pretty close. Astronomers have also found that occasionally we get meteorites falling to Earth. Maybe you've heard of that. We can pick them up. We can analyze those. We find something very interesting. The very oldest meteorites are a little bit older than 4 billion years. Why is that the case? Well, simply put, really all rocks on Earth can be affected. They can be changed. And there's very, very few that are 4 billion years old. So what that's telling us is that those are really a very small remainder, again, of what really took place, but the meteorites have not been changed. Some of those have been in outer space since the very beginning of our solar system and have only now fallen to Earth. We can pick them up, analyze them. And what we find there are ages of approximately 4.5 billion years old. So we take that now as the age of the solar system, which implies also the age of the Earth. So that really is how scientists can tell you not only how old the Earth is, but how old our solar system is by radioactive decay. Well, I'll just mention that I've done a number of videos, not only for my classes, but also for the public. Anyone at the college or even outside is welcome to view them on YouTube. My most recent one, done in here in November, was on the Earth. While I didn't go into this particular topic, if you found it interesting, you might like to go view that. It's recently been posted. We'll give you the URL for that. But for any of the other ones that might interest you, you can simply go out to YouTube and type my name in, and you'll find some other very interesting astronomy presentations.
Have you always been curious about the science around you? Submit your question and it could be featured in one of our upcoming videos. Visit cod.edu/STEM and click on So That Explains It.